Okay, fellow students, now we are going to talk about planes. So first one is the vector equation of a plane, written like this. You may notice it's similar to the vector equation of a line, but now it's got two parameters and two direction vectors. This is very obvious, as you know, planes are two-dimensional things, and lines are just one-dimensional things. To describe an actual dimension, you need an actual parameter. And for the parametric equations, it's basically the same thing. You just write out the components of each direction separately. So x will be x0 plus lambda a plus mu a. And now we are going to talk about the norm of a plane. This is crucial for us to get the Cartesian equation of a plane. So if r equals r0 plus lambda v plus mu s is the vector equation of a plane, then we define another vector n equals v cross s. It's a normal vector to the plane. This means n, this one, get from v cross s, will be perpendicular to the whole plane. It just basically points directly up or down. And the vector equation of a plane can then also be expressed in the normal vector. We have this equation, n dot with r minus r0 equals 0. Why? Because r0 is a non-point on the plane, and r is any point on the plane. So if we do r minus r0, for you to do vector subtraction, you just do the minus of the r0, which is going through this direction, takes you back to the origin, and then you go with the direction of r. So r minus r0 will be this vector here. And this vector will always lie inside the plane. And if you dot with the vector n, which is perpendicular to the plane, the dot product between two perpendicular vectors will always give you 0. And the dot product is also associative. So this means you can just expand the bracket and take this thing to the right hand side, and you get this r dot n equals r0 dot n. It's a very elegant equation, very short. And if the normal vector is n equals ai plus bj plus ck, and the plane passes through the point p of x0, y0, z0 is basically this point here, then the dot products can be expanded and give the Cartesian equation of a plane. Doing the dot product, just pair up the x and y and z components. So this times this times this, and this times this gives you this. And for this thing, it's just a bunch of constant times together, because ax0 and by0 and c0, these are just all scalar numbers. You know them all, and you just can group them all together into another constant d. So this will be the full general Cartesian equation of a plane. And now let's do an example, get you to know what the equation of a plane really looks like. Find the Cartesian, vector, and the parametric equation of the plane with the normal vector 1i plus 2j plus 3k, and which passes through the point -1, 2, 4. So this one is the non-point here, and this is the normal vector. The normal vector is just giving you a direction normal to the plane. You can place it anywhere in the plane you want, so you can also place it there. So for the solution, the normal vector and the non-point is given to us. So for the Cartesian equation of the plane, it's very easy. We can just use the formula and substitute the number in. In this case, a is 1, b is 2, c is 3. And we just substitute all the numbers in. And for x0, y0, and z0, we do the same thing, just substitute them all in. And now we can simplify the right hand side. This is -1, this is 4, this is 12. And then after all, you will get x plus 2y plus 3z equals 15. This is your Cartesian equation of the plane. And secondly, to find the vector equation, we need two vectors v and s in the plane, which means they are perpendicular to the normal vector. And what does this mean? Is their dot product will be 0. And if we just let v equals vxi plus vyj plus vzk, and then we dot it with the normal vector given to us, and this will all be 0. For the dot product, you just multiply the corresponding elements in each components and add them all together. So this times this, this times this, this times this equals 0. And you may be wondering, how are you going to solve this equation here? It's got 3 unknowns, and we only have 1 equation. But it turns out, for those type of scenarios, we can just let 2 of them into whatever we like, and then simplify it. So, as the vector equation is not unique, we can just set Vy, this thing, equals to 1, and Vz equals 0 without loss of generality. This one is a special case. You can just let these 2 numbers into whatever you like, but just don't let them all equal zeros, otherwise you are going to get the 0 vectors. And now we get this equation, which means Vx is -2. And then you may be a little bit confused now why this method works. For now, you just need to bear with me. I'll explain why it works at the end. Now we got our v here, just substitute our values in, because Vx is -2 and Vy is 1, so it will be -2i plus 1j. And we can do basically the same thing for the other vector s. We get this exactly same equation as last time. It's the same one as this, just substitute s for v. And this time we set sx equals 1 and sy equals 0 to prevent the vectors from being parallel. So we can't do the same thing as last time, otherwise we will get the same vector. And now we substitute this 1 and this 0, and we solve for sz. After that, we get sz equals -1/3. So we got our another direction vector here. The vector equation will therefore be, this is the general formula, and we just substitute all the things in. This is non-point, this is v, and this is s. Notice here I use the ijk notation here, not the column vector one. Just because ijk notation saves me space. And we have the position vector of our known point, and the direction vectors, the 2 here. So the parametric equation will then be, is the formula, and we just substitute the number in. This 3 is the known point, and these are the parameters. So when finding vectors in the plane previously, we could also set Vx equals to 1 and Vy equals 0. So back in then we have set Vy equals 1 and Vz 0. If we use a different substitution, we would get another valid solution, and although the parameters will be slightly different. And this reflects the fact that there are infinitely many vectors v and s in the plane that satisfies v cross s, which is mod v mod s sine theta equals n. As you can see from this figure, if you just rotate s and v in the same angle, which will keep the angle between them the same, when you do the cross product, you will get the same normal vector out. And which is why there's no vector division, as you cannot get a unique answer for the inverse of vector multiplication. So to make our life easier, we usually set one of the components 1 and the other 0, and solve for the third component. You can set them to whatever you like, but just don't make them all 0, because we don't want 0 vectors of our direction. And that's all for today. Thank you guys.